我想问个问题，
好，
就我想问说，因为你在算的时候，我们会低估那个 mean field 的 partition function 嘛？那它的有效范围到底在哪里？我一直很好奇这个点，
嗯，你说低估，你
因为
是指这个
就是
这个方
对
式吗？
对，
嗯，理论上你只能说，如果你取得很接近呃真实的解，就是你选了一个 reference H0，然后它非常接近你的真实的解，你只能说它很接近，但是你没办法讲它就是解。所以其实这中间有一个逻辑上的问题，就是 mean field theory 可以告诉你说，OK，这个东西看起来很像是我们要解的 interacting problem 的 solution，但是我们怎么去 justify 它看起来很像，是说它很靠近这个真实的 partition function。但是你刚刚讲问题 exactly 就是为什么 mean field 很广义，但是它会出事的原因，因为很靠近不代表物理上它就会给你类似的行为，所以 mean field theory 它有可能会给你本质上错误的结论。所以说，你能做的 approach 会比较接近是，如果今天你是面对一个你不知道的问题，你能做的 approach 比较像是我们 try our best 去 argue 说我们觉得哪些物理机制是重要的，然后我们把这个重要的物理机制利用我们知道的 H0，就是这个 reference 的 Hamiltonian 去刻画它，然后我们试着把这个 mean field 做出来以后，我们去问说它是不是给我们一个自洽的解，自洽就是它必须要 internal consistency 这第一件事。然后第二件事情是你得到了这个 mean field 以后，你要知道一件事情是像我们刚刚提到的，其实我们有忽略一个，我们有做一个近似，就是在 mean field 的阶段，我们说这个 fluctuation 必须要很小，所以有点像是说，当你做完这个近似以后，你总是要回去检查这件事，这个 fluctuation 很小的这个假设是不是合理的？因为有的时候，即使你得到了一个 self consistency 的解，但是你去 evaluate 你对应到的 fluctuation，你却发现它不是很小。那如果发生这种事情的时候，其实你就要对你的 mean field 产生怀疑，就是即使它看起来好像 OK，它非常接近我们要的这种就是 partition function 的上限，但是有可能它还是不太正确。而且就像我刚刚讲的，除了这个以外，不管怎么样，就算所有的 pass， 所有的就是 criteria 都通过 mean field theory 它本身就有一个问题，就是很接近的 partition function 并不代表就是它 capture 到的物理就是essentially 就是你抓到 qualitatively correct 的物理，这件事本身就没有到那么 trivial。但是在一般的简单情况下，大部分情况它都是很好，所以说我们会可以讲说哦，就是在一般的 physical 的情况不要太奇怪的时候，我们做 mean field 其实都可以给我们一个很好的 physical picture， 说 OK more or less 它是发生什么事。但是也是因为这样，所以你对 mean field 的结果你不应该100%相信，你只能说它提供了你一个story，就是给了你一个讲故事的框架，去强调你觉得重要的物理机制是什么，但是并不代表这个真物理机制就是100%就是这样。那从纯理论的角度，它本身就有一个逻辑的落后。那真正要 confirm 这个结果，通常你需要很多不一样的 approach。比方说，你可以暴力的用电脑数值模拟，或者是你就是找一个真正的实验，然后它很接近你要讨论的物理，然后去问他们是不是真的定性上你该看到的现象都有看到，然后要结合理论实验还有数值模拟，你才真的有办法把 interacting physics 到底发生什么事搞清楚。这也是为什么 interacting system 通常很困难，因为 在解析的角度我们能做的事情不多，然后你在数值的计算上，因为它 interacting 所以它也不好做，然后实验上因为它是 interacting system， 所以大部分时候你不会有很好的physical picture， 你该量什么，所以说这三个都很难，然后它如果又对得起来又更难，但是如果真的对得起来，你就会觉得就是非常有成就感，这样大概是这样的概念。有，请说。
就是那个 transfer matrix 的地方，你可以回到那边。
可以，让我拉一下。是这里吗？还是要更早？
对，这边为什么那个地方是 k 加 h？
你是对正负号有问题，还是你觉得应该是2或1/2？
就是2h
啊，一开始是2h， 对吧？就是如果我们只看一个棒的话，它会有这里有一个有 h， 这里有 h 嘛，对吧？这个是 transfer matrix 定义在 di 和 di 加1个 side。但是如果你去看在 di 减1和 i 的 side， 你会发现你的 transfer matrix 也会有2个 h， 一个是 i 减1，一个 i。可是因为你要 sum 的所有的 configuration， 你要把所有的能量加起来。但是如果你真的用 2h 的话，你会发现 di 个 side 你算了2次，你在这里算了1次 h， 然后这里也 h 嘛，所以 2h， 然后在这里你也是算了1次，所以你会变成你算 i size 算了2次。那可是你不希望发生这件事，因为这个有点像是你数了2次你的 Boltzmann factor。所以说我们一开始的时候用这个 approach 只是想说就是先让大家有一个大概的概念 OK， 你是真的可以有机会可以把它斗起来的，但是你也发现它有一个不太 consistent 的地方，就是你 energetic H 被数了2次。如果你要把它对应回来真正的 Hamiltonian， 所以你需要做一件事情是你的 H 你不要数2次，你数1次就好。那这样子的话你就不会出现这种 double counting 的问题。就是其实这个 H 意思是说，如果换另外一个角度讲，你有 i 加1和 i 减1的 site 嘛，然后你的中间都是用 transfer matrix 连起来的。那这个一个 matrix element 其实对应到的是你去写2个 spin 的那个 Boltzmann factor。所以这2个 spin 的 Boltzmann factor 如果总共是 h， 那表示每个人分h， 也就是说这个 spin 我拿h， 然后 i 也拿h， 对 i 减1 i 这个 transfer matrix， 然后对 i 加1这个 transfer matrix 我也是 i 拿h， 然后 i 加1拿h。那这里你就看得出来就是为什么这个应该要是 h， 因为你会发现这个加这个就刚刚好是 h， 就是这个 single site 它在有磁场下面的能量效应 exactly 就会是 h。 所以说你如果是 open boundary condition， 你就会发现哦糟糕，在角落的这2个家伙它会是1/2，所以就没有办法兜起来。可是如果你是 periodic boundary condition， 你就可以再把这个再接回来，那它就会再得到另外一个h， 那就每个人都很高兴，就是大家都分到刚好 h 的 energy， 然后你的 transfer matrix 又每个人都长得一样，然后你就可以直接把它乘起来，就整个都变得很简单。这样有回答到你的问题吗？刚刚是伟勋吗？还是我断线？
对，有回答到。
OK， 好。Okay, so hi everyone. I will continue our lecture. During the break, there are some good questions, so I'll just describe that again. The first question is about the transfer matrix. That when we construct the corresponding Boltzmann factor by putting those Boltzmann factor in the corresponding position of the matrix, we realize that we should have a Boltzmann factor exponential k plus 2h when the two spins are aligned with the magnetic field. However, when we try to construct the transfer matrix expression of the partition function, we said that the transfer matrix should have Boltzmann vector at the corresponding position to be exponential k plus h instead of 2h. Why it is so? The reason for that is because when we try to construct the Boltzmann vector and express it in this matrix form, actually we did not consider the case that there's another bond just nearby might share the same site with the previous bond. For example, initially we are constructing the matrix that describe the Boltzmann vectors for the bond that connects site I and site I plus 1. If we try to construct the similar matrix but connecting the site from I minus 1 with site I, we realize that the energy cost on the site I actually is counted twice. And because of that, we don't want to double count the energy contribution of our Boltzmann vector. So what should we do? So we said that maybe a simple fix is that we just adjust the coefficient of our Boltzmann vector from 2 to half of it. So that's why we reduce that to exponential k plus h in the transfer matrix instead of using exponential k plus 2h. So somehow it solved the problem of double counting for the site I. But if we consider the case where we have an open boundary condition, then the two ends actually will only get half of the energy from the external field. So that is not good also. So we make the second adjustment. We said that in order to have a nice expression of our partition function, we consider a periodic boundary condition such that the last spin is also coupled with the first spin. And if we write down the Boltzmann vector for this particular bond, then we can have a basically very regular expression as we just described in the lecture. So that's one way to think about how we derive this vector exponential k plus h instead of 2h. Another way to think about that is that because we are trying to find a description of the bonds using this matrix, and because as we just discovered that every site will basically be connected by two bonds, so the energetics for that site, which is the due to the external field, should be halved if we want to consider the bond in a successive pattern. So each site will take half of the energy due to the external field. So when you have two bonds, then it basically fixes the factor of 2 such that on every site they take the corresponding energy h. Okay, so that's one of the question. And the other question is related to the mean field theory of the variational approach. So here we just give a lower bound. Not this line. Let's see. Here. Sorry, not lower bound. Here, what we are saying is that there's a real partition function that we want to solve. That is the target, which is the interacting systems partition function that we don't know how to solve yet. So we said that maybe we can try to find the reference Hamiltonian, which gives us the reference partition function, and times this a little bit weird looking factor. And if we define this whole object as the mean field partition function, this inequality suggests that when we try to pick a reference Hamiltonian, we will get the corresponding mean field partition function, which will always be smaller than the target partition function, which is in interacting one. So it seems not very satisfactory because we are just saying that it is smaller than the true solution. How to justify it is the true solution? And it turns out that at this moment, you cannot really justify that. All you can do is you can check whether the reference Hamiltonian can give you a self-consistent solution. And even if you can find a mean field partition function that is very close to the target partition function, you can still logically, you cannot still say that you find the qualitatively correct physical picture to understand the interacting system. The reason is because the logic just does not work, because you just get a Hamiltonian to some extent have a very similar distribution with your system, but it doesn't necessarily say everything is reproduced on a qualitatively correct fashion. So that's the subtlety of the mean field theory. Even though it is very powerful, you can use it to basically solve various interacting problems, and it is versatile that you can adjust it under different kind of situation. But the problem is that the final result could be qualitatively wrong. So let me make a very quick statement. So from the previous one, we used the Weiss mean field theory. And here we are using the variational approach, but basically the idea is the same. But variational approach is just a more general framework. But let's just look at the result of the Weiss mean field theory. So here I didn't really solve the self-consistent equation, basically this equation. But if you try to plot that as a function of m, you'll see you basically are trying to okay, so let me try to just draw it. So the left hand side of the equation is basically m, so it's just a straight line, and the right hand side of the equation is some hypertangent function. So let's assume the external field is 0, so it's easier for us to draw it. Okay, when external field is 0, basically the hypertangent function looks like this. So if we want to find the self-consistent solution such that the left-hand side is equal to the right-hand side, basically you'll find 3 possible values of m. So usually you'll just say, so this is the, when there's a non-zero solution, it means that basically the system is allowed to have non-zero magnetization. And we said we enter the spontaneous symmetry breaking phase because currently H is set to 0. But now you can notice that when you try to change the temperature, what you are changing is actually how the hypertangent function behave. So at a critical point where you will have a hypertangent function that just cut this straight line in one point. So when the temperature is lower, you can see that you can always enter this type of hypertangent curve, and you can always get some non-zero solution of the spontaneous magnetization. And the worst part of the mean field theory is that it does not give you any information about the dimensionality. You can realize that what we just described the previous by solving this self-consistency equation actually does not rely on the dimensionality of the system in a qualitative fashion. The dimensionality of the system only kicks in through this coordinate number, which is how many neighbors each spin has, but it does not change the qualitative behavior of the system. So why it is a bad thing? Because in one dimension, we know there's no finite temperature phase transition. But if you develop the mean field theory for the one-dimensional system, the only thing you need to change is that this basically set this z by 2. But the qualitative behavior of this hypertangent function is still the same. Under low enough temperature, you will see spontaneous symmetry breaking. So in 1D, when you apply the mean field theory to the Ising model at h equal to 0, you will get a completely wrong answer, because it will basically give you the prediction there should be a finite temperature transition. But in fact, there's no such finite temperature transition. And the reason for that is basically in one dimension, as we described, this the anticipation that most of the spin will prefer to align more or less in some direction with a little fluctuation is not a correct intuition, because as we argued previously, you can create this domain wall, and this domain wall is free to move inside your system. So basically, entropic effect will always win. So the fluctuation for the spin is actually high, and it is not something that's small. Okay, so that's basically the two questions. And now I'm going to continue our description about the variational approach of the mean field theory. So at this moment, as I just described, what we did is that we use a very simple inequality, basically this one, and using this simple inequality, we can derive the variation relation of the interacting Hamiltonian and the mean field Hamiltonian. So now we want to ask if we know what is the relation, oh sorry, not Hamiltonian, the partition function. We got the relation between the partition function of the interacting system and the partition function of the mean field theory. So if we have that relation, it is tempting to ask, how about the free energy? And it turns out the free energy is also, at least formally, it is simple for us to write it down. The true free energy is just minus kBt times the nature log of the interacting partition function z. And because of this inequality, we know that the true free energy must be smaller than the mean field free energy, which is derived or defined by minus kBt times nature log the mean field partition function. Okay, so what we are trying to do is that we are trying to find expression of the mean field partition function, and we are going to use variational method to find the minimum of this free energy. And if we can find that minimum, we argue that maybe it is very likely that this mean field theory capture the essential physics and reproduce the physics of the interacting system, at least qualitatively correct. So now the test case, how to evaluate this thing. So we basically what we need is the nature log of this stuff. So I'm not going to do that explicitly here because it should be quite straightforward. And it turns out that after you perform this evaluation, you'll see the mean field free energy. Basically, it looks like this. So what does it mean? It means that the mean field free energy has two parts. One is from the entropy of the reference Hamiltonian times the corresponding temperature, and the other is the interacting Hamiltonian evaluated using the probability distribution derived from the reference Hamiltonian. So that's why this expectation value is would have the sub-index 0. So let me emphasize that. Okay. So that's it. So let's take an example again, our Ising example, to demonstrate how things work. So the first step is we choose a reference Hamiltonian, which is now has a variational parameter lambda, and the Hamiltonian is simply the Hamiltonian with external field like form. So basically this lambda is like some kind of external field. Okay. So for this reference Hamiltonian, it is easy for us to evaluate the magnetization, which is let me try to write it down. It is defined as the value m, and by definition, it is the number of up spin subtract the number of down spin divided by the total particle number n. Okay, so that's the stuff that we need, and because as I mentioned that the variational parameter of our system or of our reference Hamiltonian should be lambda, but there's a one-to-one correspondence between lambda and m. So we are going to take that advantage and later express the result using m. So let me take a remark. Okay. So now we want to evaluate two things to get the mean field free energy. The first thing is the energy of the interacting Hamiltonian evaluated using this reference Hamiltonian. So let me just write down the general expression. So formally, that's how it looks like. So here we are going to use the property that the reference Hamiltonian is basically a non-interacting Hamiltonian, which means that the distribution function of the system actually can be considered as a product of the distribution function on each side. So what do I mean by that? Is that the distribution function of all the spins actually can be expressed as the distribution function on side I of spin I, and try to form a product of all of them. So because of that, this expectation value of the SI/SJ term actually can also be factorized. Maybe I should put this line here. Okay. So once we have this step, then we can notice that by definition, the expectation value of SI on this with the reference Hamiltonian is just M. And we can simply express it by, so this product is just M squared, and we just need to count how many bonds that have this property, and it turns out it will looks like minus J times M squared times Z divided by 2, and we will have n of them for a system with n spin. And the reason this is Z divided by 2 is because for every side it will have Z neighbors, but whenever you count the number of bonds according to the site, because we multiply we multiply the number of sites outside this square bracket. Whenever you do this counting, you'll find that every bound will be counted twice, because every bound will connect two sites. Because of that, there will be a factor of 2 need to be divided. Okay, so that's the first term. And the second term is, again, simple, minus h times m, but you have n of them because we have n sites. So let's just put them together inside the square bracket. Okay, so that's the first part, the energy as a function of the variational parameter m. So now the question is how to evaluate the entropy when the variational parameter is m. So this is again a calculation that we have done several times. So the entropy is basically kb times nature log. You choose n spin up spins inside the n sites. So it will just give you kb nature log n factorial divided by n spin up factorial and m minus n spin up factorial. So that's the entropy. At the system, as the system reaches thermodynamic limit, we can basically use the Stirling's approximation. And we will find this entropy will be n times nature log 2 subtract 1/2 1 plus m nature log 1 plus m plus minus m h log minus m. Okay, so now we are in business because now we have the expression for entropy for the reference Hamiltonian with a variational parameter m, and we also have the energy of the interacting Hamiltonian evaluated using the reference Hamiltonian. So now we have the free energy expression and the free energy density as a function of t, and the variational parameter is defined as the free energy divided by the system size is basically minus 1/2 jm square jz m square minus hm and minus kbt times h log 2 subtract 1/2 m h log m, and the other term that is going to be useful to get the hypertangent. Okay, so this is the free energy density when we use this approach. So sometimes this theorem or this description is actually derived by Bragg and Williams. So sometimes you'll see it is the Bragg-Williams theory. Okay, so now we have our free energy density. We want to find the minimum of it, or we want to do the variation with respect to the variational parameter m. And you will see this thing goes like this. And this part is the hypertangent h of m. And for the minimum of the free energy density, we require this variational equation to be 0. So if you shuffle those terms, you'll find it is again the self-consistency equation that we derived in the Weiss mean field theory. So at this point, are there any questions? Okay, so let me try to re-express this approach. The variational mean field theory is a approach based on this simply trivial inequality, and we formally rewrite the partition function as some kind of partition function of our reference Hamiltonian. At this moment, we don't know what is the reference Hamiltonian. It will affect our expression in two ways. It will affect the basically the most important part is that it will affect how we evaluate the interacting system using this reference Hamiltonian. So in principle, there are various different kinds of reference Hamiltonian. How to choose the reference Hamiltonian actually depends on our physical picture. So here we use Ising model as an example, and as we described, we know that, or we anticipate that Ising model should have a limit, at least at the low temperature limit. It will behave very similarly as if all the spins are aligned. So it is very tempting to find the reference Hamiltonian as all the spins are aligned by the magnetic field lambda, which is the variational parameter for this example. And for this simple reference Hamiltonian, we actually know a lot of things. One of the important things that we know is that the expectation value of the spin can be defined as the magnetization, and there's a one-to-one corresponding relation between the magnetization and the corresponding field, which is the parameter lambda. So as we mentioned, we want to perform the variational approach to approximate the true partition function. In this reference Hamiltonian, the variational parameter is this lambda, but because of this one-to-one correspondence, equivalently, we can try to vary the magnetization. So now the question is how to evaluate the necessary ingredients using the magnetization. And what we found is that it is not too difficult. The most important step is that because the reference Hamiltonian we choose actually can be factorized. So when we evaluate the interacting terms, it can be simply factorized into the product of the magnetizations. And because of that, we overcome our first obstacle, basically how to evaluate the interacting Hamiltonian using the referencing Hamiltonian. And then the second obstacle is how to evaluate the entropy for the reference Hamiltonian. And because it's a relatively simple system, so we know that the variational parameter M can build a simple relation with its entropy through the following fashion. So we put those information together, then we got our free energy density. And if we do the variation and find the first derivative to be 0, we got the self-consistency equation. So this is one approach to solve this variational mean field theory. However, there's another approach. The difference came from the fact that before we enter the Ising model, like right above here, it is basically the formal approach. It doesn't tell us that you can always find the one-to-one correspondence between your reference Hamiltonian and the variable that is essential to describe your interacting Hamiltonian. So in principle, there are other ways to perform the variational approach, but the idea is that you do variation directly on the distribution function of the reference Hamiltonian. But that will require more evolved discussion. So I will skip that and leave it for the reader who is interested to explore that. The reference will be posted on the lecture note website. Okay, so that's basically the mean field theory. So at this moment, I think we set the stage to have a teaser about the Ginsburg-Landau theory. So if we look at this free energy, and we again focus on the case when h equal to 0, the free energy density will actually look like this. And also, if we make the further assumption that m is about 0. Okay, at this point, it is not clear why we want to make this m approximate to 0 approximation. I'll try to describe that now, because as we described, when we change the temperature according to the mean field theory, we found that at 0 temperature, it will have some finite value, and there will be a critical temperature Tc. After that critical temperature, the magnetization becomes 0. So that's like roughly something like this. Okay, so deep inside the phase, we will expect that the fluctuation is not too large. They are just, a specific phase. So the part that mean field theory actually might not work that well is when the order parameter, to some extent, or the magnetization nearby the critical temperature might fluctuate wildly. So when will that happen? It will happen when the magnetization is relatively small. So you can do this expansion and try to expand the free energy expression, and it turns out if you do that, you will find the following expression. And if we try to collecting things, we will have first have some constant term, and we will have a quadratic term, and we will have the quartic term. And also ignore what's happening later because m is small. So if you try to plot the free energy density as a function of m, you'll realize that the behavior strongly depends on the sign of the quadratic term. Because of that, let's call this Jz as the temperature scale kBTC. So we immediately see there will be three behavior. Wait. This is the case when T is greater than Tc, and T is equal to Tc, and T is smaller than Tc. So when T is greater than Tc, it means that the coefficient of the quadratic term is positive. So we have something like m squared plus some m to the fourth. So basically you just see something that's just a polynomial, but I'm not drawing it nicely, but you get the idea. So when t equal to tc, basically we have no quadratic term, we only have the quartic term. So it will be a shape that has a flatter bottom. So when t is smaller than tc, then we have something with a negative coefficient of the quadratic term. Then you will see something that looks like this. So when you are doing the variation, you'll see there's only one solution when the temperature is higher or equal to the critical temperature. But when you are lower than the critical temperature, the variational equation will give you two minimums. So that's good. And because of that, if you just look at this expression of the free energy, you'll see if you try to derive what is the corresponding minimum value, what you need to do is you need to take the free energy and make a variation with respect to m. But now we take, instead of the hypertangent function, we take this equation as small m. Then what you will find is that, let's see, can be t minus tcm. M plus, I think it is 3, right? Yeah, and kb t m cube. Okay, that's when you take the first derivative with respect to m. And from this equation, you immediately see m is equal to plus or minus square root of 3 tc minus t divided by t. Okay, so which is proportional with tc minus t to the power of 1/2. So this is the critical exponent for mean field theory. Oops, what's this? Okay, so so now we have a better understanding about the phase diagram. Basically, this is the temperature and this is the magnetization. And as I mentioned, the order parameter will be robust, and then you will decay to somewhere. Once it hits to the critical temperature, the order parameter gets 0. So here's the Tc. So what we just derived is the critical behavior nearby Tc actually will goes like this. Okay, so that is nice. So what exactly is the Ginsburg-Landau theory? Basically, we just derive a very simple version of it. The idea is that wait a second. The idea is that even though we are using this very simple model and we derive everything through detailed calculation of the mean field theory, what Landau is trying to think about is that is it possible that would have a bigger framework that we can directly guess or argue the form of the free energy density as we had in this line nearby the phase transition. And the reason that it is a good question is because we might have various different kind of interacting systems, and maybe one way is that we run the mean field derivation for every one of them, but once you perform that kind of calculation several times, you will realize that there are some pattern or there are some structure within the mean field theory. One of the important structure is about the symmetry property of your system. So for the Ising model, when there's no magnetic field, we know that the system has the Ising or the Z2 symmetry. So we also use the magnetization which break that Z2 symmetry to identify whether we enter this order phase or not. So Landau's idea is basically saying that maybe we can try to think about this magnetization in an abstract sense, saying that there's some parameter that can characterize this order, and because of that, this is called the order parameter. And this order parameter needs to satisfy several conditions. The first is that it needs to be a local object, which means that you can define it with the information within a region of your sample. And then once you define this local order parameter, which break the symmetry of your system, you want to ask how to use this local order parameter to construct a free energy which should respect the symmetry of your system. And in this simple example, because this magnetization, which is the local order parameter, breaks the Ising symmetry, in order to have the correct Ising symmetry recovered, we always require the magnetization appear in even powers of the m, because that's the algebraic structure such that when m goes to minus m, the free energy density will not be changed. So it's like the very quick and motivation about why Landau's theory is going to be useful, because once you use this argument, even though you don't know what is the exact coefficient in front of those terms, but it doesn't matter, because you know from the mean field theory, the quadratic term 1 will have a sign change when you cross the critical temperature. Then you can use that to argue that whether a certain type of phase transition might happen, even though you don't know what is the exact coefficient, but you treat them as a phenomenological constant and try to adjust them to fit the experimental data. So that's the idea of Ginsburg-Landau theory, at least at the motivated from the mean field theory perspective. However, I need to emphasize that is not the whole story, because the fact that Landau's theory require the order parameter to be small also suggests that the fluctuation nearby the critical temperature might overwhelm this criteria, and how to deal with this fluctuation it's a very important question. And also, there's a very big problem for Landau or for the mean field type approach is that whenever you use Landau theory or you use mean field type theory, the corresponding critical exponent for the system, usually, especially for the this particular critical exponent, which is beta, beta will always be 1/2. So that's a problem because in the experiments, they are able to measure this critical exponent and they found some systems that does not have these 1/2 critical exponents. That's one thing. And maybe you'll say, oh, there's just some imperfection in the experimental conditions, so maybe we should not care about this discrepancy. But the most dramatic effect came from the exact solution of Ising model due to Onsager. What he found is that basically he solved the 2D Ising model exactly, and it turns out that here we just use the mean field theory to describe the 2D Ising model, and we found the critical exponent to be 1/2. But the exact solution tells us that the critical exponent is another value, not this 1/2 value. So that leads to a big question mark that how to bridge the result from the exact solution and the approximation that is made by mean field theory. If we can do that, then we basically have a complete story about how to understand the phases and phase transitions. But as you probably already noticed, this is our last lecture. We probably will not go further than this. So if you are interested, you want to explore some further information about how these critical exponents can get modified from some theoretical framework, please take statistical mechanics 2. It will be important because it turns out that this seems like quite unimportant difference between the critical exponents actually leads to a big story about the Nobel Prize. That's the idea of renormalization group that is fundamental important for both condensed matter physics and particle physics. And it turns out it is so important because to some extent the concept of renormalization group is a theoretical structure for various different theories. So I think I'll pause here, and the semester basically ends here. And if you have any questions, you are welcome to ask, and I'll try to answer that. And I need to remind you that there will be a homework due this week, and the final project will be due next week. And if you have some late homework, please try to follow the timeline unless you send notice to me, because it is the end of the semester. For those homework that is late, we can only accept very short delay. So that's basically the end of the semester, and hope you have a nice final exam week, and hopefully you have a great summer during this pandemic time. Okay, see you. And if you have any question, you can just unmute yourself and ask.
老师，我想问，喂，老师，
嗨，请问。
我想问说，为什么它是正比于 Tc 减 T？它下面不是还有个 T 吗？
它会有一个 T 啦，但它不会爆掉，所以我们就不太在意它。就它不会有变成0或爆掉的行为，所以就是某种程度上它就是一个 比较像正常的数字这样，所以我们通常不太会管它。
你是说因为那个 phase transition 的速度极快嘛？
应该说就是你想就是我们的 magnetization 是变小的嘛，对不对？就是如果在 TC 附近，那什么东西会变小在这个 expression 里面？基本上只有这个家伙会变小，当你的 T 靠近 TC 的时候。所以你想问的事情是，当你 T 靠近 TC 的时候，因为 T 靠近 TC， 我们假设从低温上来，因为你如果是从高温，它一直都0嘛，所以没有什么用。但是如果你是从低温，就是这样讲好了 ，T 是从 TC 也就往 TC 负靠过去，那你会发现这个上面这个东西是慢慢变小，下面这个东西它是慢慢变大的，它就是慢慢的往 TC 靠过去。可是问题是它慢慢变大，对我们来说不是太重要，因为我们想要知道的是你的 magnetization 怎么变小的，所以变小的那个部分是我们比较想要的资讯。所以某种程度上，你几乎可以把这个 T 就想象就是反正我都是在 TC 附近嘛，因为我在意的是它怎么变成往0的地方靠近，都在 TC 附近。你几乎可以把这个 T 就直接当成它就是 approximate TC， 就把它当一个 constant， 所以你只需要看这个部分就好。
好，了解。那另外的就是我不太懂那个 Fermi energy，那个 free energy 的那个，你推导的时候你直接取，为什么它可以直接写成 H 的平均减 TS？我觉得那很不直观，是直接取
哪一个？
就 T 减
再往上嘛？这个吗？
对。
这个你需要做一些事，然后这里为什么有一个红线忘记了？管它，我直接写好了。就是
你说那个就是 general 的形式啊，下面是举例子。
你的问题是这个吗？
对。
OK， 这个东西其实是可以导的，只是因为时间的关系，所以我就直接跳过去。就是其实你要做的事情就是 evaluate 这个，所以是负 kBt 乘上 nature log z mean field。这个家伙都一直待在那边，所以我们就先不要管它，就是我们就 focus 在 z mean field 在做什么就好了。
所以它就是 z0 乘上后面那一串平均的东西。
对，基本上 z 就是这个东西。OK， 好，那我们就看一下它是怎么 evaluate。所以我们会有 nature log z0 嘛，然后加上这个是负贝塔这个东西。这样对吧？好，然后接下来下一个问题就是我们要问怎么样去 evaluate nature log z0， 因为我们会想要得到somehow 和 S0 有关的资讯，对吧？好，那接下来我们要用的 condition 就会是我想一下OK， 所以其实我们还是有负 kBt 在外面嘛，所以说是这整坨其实是乘负 kBt， 然后这个乘负 kBt 就不见了嘛，所以就会我们会得到负 kBt， 那就有个 z0， 然后负 kBt 跟贝塔不见了，所以是加点加上 h omega 0，然后减掉 h0 的0 ，OK。好，然后接下来我们这里会用一个条件是 nature log z0 是什么意思？就是 z0 这个系统的partition function， 其实它对应到就是 z0 这个系统的 free energy， 那就这整坨就是 z0 的系统 free energy。那基本上 z0 的系统 free energy 就是10减掉 t 乘上 s0 嘛。那10是什么？10就是 h0 在0的地方的 evaluation， 就用0去 evaluate h0。我在讲什么？用 h0 这个东西的 distribution function 去 evaluate h0 的平均值，那你就会发现这个和这个会杀掉，然后活下来就只剩这个和这个，所以你就得到这里这个 h 应该要加 omega， 如果我刚刚 notation omega 的话，对，这里应该有 omega， 就是 interacting 和 Hamiltonian 在0的地方，就用 non-interacting 的 Hamiltonian 的 distribution function 去 evaluate 它，然后你会减掉一个 TS0 在这里，就这样。
你那个 H omega 是你新的 Hamiltonian，就是你
H omega 是有 interaction 的 Hamiltonian，
就是 interaction 的 Hamiltonian，H 零就是没有 Hamiltonian，
对
没有
H 零是一个你拿来当做起始点的，通常我们会挑那种我们非常了解怎么解它的 Hamiltonian， 也就是通常都是 non-interacting Hamiltonian。像我们刚刚的那个例子 Ising 的话，我们的 H 零就特别选了一个，就只有external
外
field，
场。
对，所以我们非常清楚知道它在干什么，所以说就用它这样，对。
所以它就跟前面的那个方法用的只是它用变分方法去算而已，就是把那个变数去算了。
对，基本上差别和刚刚的这个做法，刚刚这个做法是比较直觉啦，就 Weiss mean field 是物理上非常直觉，就是说OK more or less 这个 spin 被拼在那边了，所以统计上它不会 fluctuation， 所以我们就直接把它丢掉，就好像它不会动。可是问题是这个做法是比较难，就是推广到不一样的系统。所以说，如果你用这种 variation 的方法的话，你就会发现哦，其实它可以非常广义。你的只要任何 H 零你可以做，你就可以这样做啊。可是问题是能不能解出来是另外一回事。那我们当然挑了一个比较简单的模型，就只有一个 single variational parameter， 就它，那就可以做。对。
那另外就是有一个 M 不是就是 self-consistent equation，
对，
你不是画那个图会有3个点，那3个点代表说我可能出现的 magnetization 的值吗？
这个吗？
对，
就是你的 self-consistent equation 意思是说你要问你的 m 是多少的时候，你的整个理论会自洽。所以说这个等号左边是一条直线，然后等号右边是一个 hypertangent， 所以也就是说告诉你只有在这3个点你才会有一个自洽的 magnetization 的值。如果你不是在这3个点，它连 self consistency 都做不到。也就是说你一开始 propose 假设我的 m 是某一个值，比方说我要怎么样评，就是 evaluate 我的等号右边，我们等号右边是怎么得到的？我们是假设我们有一个 effective Hamiltonian， 然后外场是给定的嘛，这个是先给定的，然后我们其实不知道这个 SI expectation value 是多少，所以说我们一开始我们都先说好，我给定一个 SI 的值。举例来说，我把这个东西叫做M star 好了，然后 M star 假设我设定它叫 0.3， 数值上就假设我现在在做数值的计算方法，我就假设它 0.3。那我如果用这一个 effective 的 magnetic field， 我去做我的 magnetization 的 expectation value， 我会得到一个值。那我怎么做呢？我就是我们传统之前知道的方法，反正它 partition function 我可以算嘛，我就把 partition function 算出来，然后我就直接去算这个东西的expectation value， 然后你就会发现你会得到等号右边的东西，然后这个 m 的值就是在 m star 等于 0.3 的时候的情况，你就得到等号右边的值。可是你会遇到一个问题，这个值算出来不一定是 0.3， 就是这个值算出来可以是任何东西，它搞不好叫 0.5 之类的。可是那你就遇到一个麻烦了，你一开始说我的 m 的值应该要是 0.3， 可是经由统计力学的这个 independent spin 计算，我得到这个 hypertangent 的值竟然是 0.5， 可是这个 hypertangent 应该要是跟 m 是一样的值，那这就遇到一个问题，这就是所谓的就是没有 self consistent， 就你的理论自己没有办法自洽。那这个图其实是告诉你说，你要让你的理论也可以自洽，基本上最多只会有3个地方啊，最少就是一个地方，就是当你在比 Tc 还低的时候，基本上它就只会有一个解，就是 m 等于0的情况。所以当然这个图是 h 等于0的图啦，所以现在看起来有点怪怪的。但如果你 h 不是0的话，它当然就会有一些改变。所以对，所以这个图最主要的功能只是讲，就是这是一个 self consistency equation 的 condition。对，
有点谢老师。
不会。
老师，
请说。
我问一个比较前面一点的问题，跟笔记没有关系，就是
好，
grand canonical ensemble 啊，是指说系统跟一个大热源，然后又是大粒子源接触嘛，对不对？那为什么没有一个东西，就是没有一种 ensemble 是系统跟大粒子源接触？是因为说，如果我们不考虑温度的话，这些粒子其实不太会有 diffusion 的问题，所以这件事情是 trivial 的吗？
等一下，我有点没听懂，大粒子源是什么意思？你是说可以交换 particle 吗？
可以交换 particle。
有啊，那个 ensemble 就是那个 grand canonical ensemble， 就是有 chemical potential 的那个。
对，可是它同时是有可以交换粒子，然后也是温度上面也有那个交换。
主要原因是因为这是一个 tricky 的问题，就是你很难有一种情况是你会交换粒子，纯交换粒子，但是你不交换能量的。就是我想一下，有没有什么情况是你会交换粒子，但你不交换能量？因为其实某种程度上，这个粒子它一定自己带某种程度的能量嘛。所以通常我会说，就是你做 grand canonical 的时候，你交换粒子，你一定会同时要引入 temperature 和 chemical potential。所以如果今天有一个情况是你可以交换粒子，但是你不交换能量，那意思就是说，基本上这个粒子必须要完全没有能量，它要不然不会动，不是要不然它必须要不会动，而且它必须要它没有 potential energy。所以基本上它是在一个 free system， 它是一个 free particle， 但是它的 momentum 必须是强烈的是0。那这种情况它可以交换粒子，然后它就不会有任何的能量损失。可是问题是，那这家伙是一个很奇怪的系统，所以好像是我觉得应该是因为这样，所以大家不太会去考虑这种情况。因为如果我们把能量也就不让它就是交换就我们希望它交换粒子的时候不会有任何能量改变的话，你就必须要这种很奇怪的像鬼一样的粒子，就是我想不到任何东西是目前的任何粒子像这一种的原因，是因为我可以想到没有质量的粒子，比方说光子之类的，但它还是会带能量。那对啊，就唯一的可能就是它不会动，然后它也不带 potential， 然后可是somehow它必须要从一个系统变成另外一个系统，我不是很确定这要怎么做到。就它要怎么离开这个系统都是个问题，因为它如果是一个粒子，它必须要有空间的概念，就是它在系统里面或不是在系统里面。那它要离开的，表示它必须要有某种改变空间的就是改变位置的能力。那有改变位置的能力，就表示它必须要是有速度的，除非它是 quantum tunnel 或干什么，它突然间从一个地方消失，然后跑到另外一个地方，要不然基本上这件事应该是不太会发生，对。But anyway， 是一个 interesting question， 只是我没有办法 came up with 更好的解释，就是这个系统该怎么去思考它。我只能说，就是说不定有些情况有可能真的需要考虑这种物理，但是目前我是没有经验过这种情况。对，
谢谢老师。
哦，不会。Oh, by the way, there are 2 questions. One of the question is about is asking about how to derive the equation that I skipped, like why the mean field free energy can be described as the interacting Hamiltonian the expectation of interacting Hamiltonian weighted by non-interacting Hamiltonian. and subtract the temperature times the entropy of the non-interacting Hamiltonian. And I think I basically did the derivation, and the key step is basically you just insert this expression into the nature log function, and you make the replacement that minus kBt times nature log z naught, which is the free energy of the non-interacting system, which should be understood as the energy of the non-interacting system subtract the temperature times the entropy of the non-interacting system. And the energy of the non-interacting system is basically H naught evaluated at with respect to the non-interacting Hamiltonian's distribution function, and you will basically cancel the second term of the exponent, and that leaves the expression. Okay, so that's the first question. And the second part of the question is about the motivation of this variational approach. The reason is that the approach of Weiss mean field theory is to some extent more or less straightforward, because we kind of have a very intuitive understanding why Weiss make this kind of brute force assumption to drop the fluctuation. However, when we are facing a unknown problem, it is not a priori clear how to find the corresponding description. So that's why I introduced this variational approach. So for this variational approach, the theoretical structure is quite general. However, the challenging part is how to choose the corresponding variational Hamiltonian or the corresponding reference Hamiltonian. That is complicated enough that it can capture the unknown problem that we want to solve, capture the essential physics of the unknown problem that we want to solve, but also simple enough that we are able to solve it. But it provides the opportunity that you can perform the related calculation by this approach to form the mean field description of your free energy, and then you try to find a variational solution for this free energy. And in our lecture, we use a really simple example where we can do the variation directly with respect to the order parameter m, which is the magnetization. However, there are some more general but complicated method that you can do variation directly with respect to the distribution function that I didn't talk about, but I will encourage everyone who has interest to explore that part. So the bottom line is the variational approach is more general, and even though we don't have a lot of more complicated example to demonstrate the point, but that's the original motivation. Why do I want to introduce that? And the other question that I ask is about what do we mean by the self-consistent equation, and why there's a weird wait, I don't know why, but seems like some kind of weird picture here. I don't know why, but anyway, let me remove it. So the question is how to interpret the self-consistency equation. So and the picture that I just draw at the left hand side. So the point is that the self-consistent equation just said at what value of the m's the theory, the mean field theory, is self-consistent. So when the two lines cross, in this example, there are only 3 points, which suggests only 3 points in the parameter space of M can satisfy this self-consistency equation. So let me take an example about what do we mean by not satisfying the self-consistency. So after we do the mean field theory, at least formally, we notice that the whole system is described by an effective magnetic field, which is the summation of the original magnetic field plus the Jz times the expectation value of Si. Okay, so at this moment, we don't know what expectation value of Si is, so we just give it a number by a guess or something. So for example, if we give it a number which is the m star, and this m star value, let's say it is equal to 0.3. So now we have a definite a value of the corresponding magnetic field. So we use this magnetic field, which is just a bunch of spins within this effective magnetic field, to construct the partition function and the corresponding distribution function. And once we have that distribution function, we use that distribution function to evaluate the value of magnetization. Then we might get some result, but the problem is this result, which is the expectation value of the magnetization, might not be the m star value that we give at the very beginning, which is 0.3. Because after this evaluation, maybe you'll get a value that is 0.5 or something. Then you have a problem because the expectation value of the Si should be the same as the given value that you provided at the very beginning, m star. If it doesn't match, it means that the theory does not have the self-consistency. So that's why most of the time when I plot this plot at the left-hand side, the self-consistency is not satisfied. Only at these 3 points, the self-consistency can be satisfied, and only at those 3 points, it is meaningful to discuss what is the corresponding physics. Otherwise, it is just a theory that is not self-consistent. And other than that, I think there's another last question is asking, when we explore or develop the ensemble theory, why there's no ensemble that corresponds to the case that the system can exchange particle but cannot exchange energy? And the answer to that is because it is really difficult, at least for me, to find an example for that where the system can exchange particle but without changing the energy of the system. So maybe there are something like that, but I just off the top of my head, I don't have an example for that, because I can think of something without mass, like photon. But for photon, when you change a particle, the photon mode carries a certain amount of energy. So definitely you will change the energy of the system. So that's the reason why I think grand canonical ensemble usually needs temperature and chemical potential at the same time, because when you exchange particles, usually the exchange of energy is guaranteed. Okay, so thanks everyone for participating. 谢谢大家参与。如果没有问题的话，在5分钟我就会把 Webex 关掉。如果有问题的话，可以现在就出个声让我知道，就是阻止我把 Webex 关掉。